Hey guys, today we're going to be talking about exponential equations. And this is where we're going to use logarithms to solve exponential equations when we can't use anything else. There's two ways to solve exponential equations, and both need to satisfy a specific equation in order to use the method. Alright, so we have the first one's method is fairly simple. So if b of x equals b of y, then x equals y. So b represents the base, whereas x and y represent the exponents. So x and y, they are the exponents. Okay? So when the bases are the same, the exponents can be set equal to each other, and we can solve. So note that this fact does require that the bases in both exponential be the same. If it isn't, then this fact will do us no good. So let's look at the first example. So we have 5 to the 3x equals 5 to the 7x minus 2. Well, are the bases the same? Well, 5 does equal 5, so we can set our exponents equal to each other. So we have 3x equals 7x minus 2, and then from here we just solve for x. So I'm going to move all my x's to one side. So we have 0 equals 4x minus 2, and then plus 2 to both sides. So we have 2 equals 4x, and then divide by 4 to both sides. So then x equals 2. I'm sorry, not 2. 1/2. Because 2 divided by 4 is 1/2. Alright. So now let's look at our second one. We have 4 to the t to the second equals 4 to the 6 minus t. So the bases, we have 4 and 4. They are the same. So we can set our exponents equal to each other. So we have t squared equals 6 minus t. And now I'm going to put them all on one side. So we have t squared minus 6 plus t equals 0. So I subtracted 6 and added t to both sides. And then from here, we need to factor. So I'm just going to rearrange this real quick. So we have t squared plus t minus 6 equals 0. And to factor, we're going to use our big X. So we need to add to 1, but multiply to negative 6. So then we have 2 and 3, where 2 is negative. So we have x minus 2, x plus 3 equals 0. And these are t's. And then we set them both equal to 0. We get t equals 2 and t equals negative 3. So that one had two solutions, but still got us the same process. So this is a little different. So we have 3 to the z equals 9 to the z plus 5. Well, if you look here, our bases are not the same, but they are in a way. We have 3 to the z and then 9 to the z plus 5. Well, 9, can we get 9 from raising 3 to an exponent? Meaning, if I raise 3 to the second, will I get 9? And that's yes. So we can change our base such that the bases are the same. So 9 we can change to 3 to the second. And so that's going to look a little bit different. So we have 3 to the z equals 3 to the second to z plus 5. So in parentheses we have 3 to the second, and we know that 3 to the second is going to equal 9. So then you're probably wondering, well, what do I do with this second? Well, we are going to multiply it to our exponent. So we have 3 to the z equals 3, and then we're going to distribute this 2 to the z and the 5, so we have 2z plus 10. And then from here, our bases are the same, so we can say z equals 2z plus 10, and then we can solve for z. So I'm going to put my z's on both sides, so I'm going to subtract 2z. And we have negative z equals 10, and then get rid of that negative 1 by multiplying by negative 1. And then I get z equals negative 10. So when we have this first method, we can double check that we can manipulate our base. So if we have something that can be raised to the power to the original base, then we can change it so that they're equal, and we can set the exponents equal to each other. So now we have our second method. This method is used when the bases are not the same. And this means if it was like we had 7 and 2. We can't change 7 or 2 to make them kind of the same base, so we have to use this when we cannot manipulate our bases. So this method is taking the logarithm of both sides. This can be the common log or the natural log. Common log meaning just the log, and natural log being ln. And we can use this formula. So please make sure you know this formula so that we can use it correctly. And then we'll use this formula to solve for the variable. Alright, so let's go ahead and use it. So for our first one, we have 7 raised to the x equals 9. And here I know my bases are not the same. I can't change 7 or 9 to get to the same base. So I'm going to take the log of both sides. So I have log of 7x equals the log of 9. And then this is where our formula comes into hand. So we're going to take the log of 7x and we're going to change it to this guy. So we're going to take our exponent and we're going to move it to the front of the log. So we're going to move our x to the front. So now we have x log of 7 equals the log of 9. And then from here we can solve for x, so we can divide by log of 7 to both sides, and then we have x equals the log of 9/7. Alright, not too bad, right? So now for our second example, we have e raised to the t plus 6 equals 2. Well, what do you remember about e? That's most commonly used with natural log. So I see right there, it is going to be 10 times easier using the natural log. So we're going to take the log of both sides using the natural log. So natural log of e, t plus 6 equals the natural log of 2. So then from here, I can recognize something about this fact. The natural log of e, if you remember, is equal to the exponent. So if we have the natural log of e to any exponent, then that will just be equal to the exponent. So what this means here is that t plus 6 is going to be left alone. We don't have to move it. It's just going to be like that. So then we have t plus 6 equals the natural log of 2. So then from here we need to solve for t. So I'm going to subtract 6 from both sides, and then I have t equals the natural log of 2 minus 6. Alright, so we have our last example. This one's a little bit different. So we have 2 raised to the 4y plus 1 minus 3 to the y equals 0. Well, for this one, I want to move my 3y to the other side so that we have our exponential equal to an exponential. So I'm going to add 3y to both sides. So then we have 2 raised to the 4y plus 1 equals 3 to the y. Then from here, I'm going to take the natural log. So taking the logarithmic of both sides. So you have the natural log of 2 4y plus 1 equals the natural log of 3y. Can't keep my colors straight. Alright, so then from here we use our rule to move our exponent to the front. So now I have 4y plus 1 times the natural log of 2 equals y times the natural log of 3. So now we're going to solve for y, just like the normal process. So I'm going to distribute my natural log to both. So now I have 4y natural log of 2 plus natural log of 2, because natural log of 2 times 1 is natural log of 2. And then I have y equals the natural log of 3. And then I noticed that this term and this term can factor out a y. So I'm going to put those two on one side and then natural log of 2 on the other. So what I'm going to do is I'm going to subtract y natural log of 3. And I'm also going to subtract natural log of 2 from both sides. So now I'm left with 4y natural log of 2 minus y natural log of 3 equals negative natural log of 2. I'm going to factor out this y. So then I have y times 4 natural log of 2 minus natural log of 3 equals negative natural log of 2. And then I'm going to divide by this mess. And then we will get that y equals negative natural log of 2 all over 4 natural log of 2 minus natural log of 3. So when we're doing solving exponential equations, remember your steps are to check the base, have them equal to each other, and then take the log slash set the exponents equal to each other. Alright, that's it for today's video. Have a good one.